Section 12.5, triple integrals, video 5. Let's knock out the third type of solid over which we can integrate a triple integral, and then we'll look at some examples. The third type of solid, I guess I should put a 3 here, is, well, I described it in the previous video. It's the natural direction to go. The first type of solid was we have a solid bounded above and below by some surfaces. The second type was we have a solid defined in the back and the front by some surfaces. And the third type will be we have a solid defined on the left and the right by some surfaces. And so when we do that, those surfaces are functions of x and z. In other words, go over to an x value, up to a z value, stick it into the function to tell you the left side of the solid, stick it into the function to tell you the right side of the solid. When we have such a solid, we would project it onto the plane that contains these two variables, x and z. So imagine a light source over here that only projects light horizontally, doesn't go off any other direction. Then the shadow would be the projection of this solid onto the xy plane. So how would we set up the triple integral? Well, the triple integral over the solid E of a function dv, we would first evaluate the integral with respect to y. Now, how do I know it would be with respect to y? Because the surfaces that define the left and the right side are functions of x and z, so I can't integrate with respect to x, and I can't integrate with respect to z. So u1 xz would be the lower limit, the lesser of the x's, and u2 xz would be the upper limit, the greater of the x's. So you would evaluate that integral, and then evaluate the double integral over the region that's the projection onto the xz plane, dA. How do you evaluate the double integral? Well, again, it depends upon how your region is defined. For example, if this region is defined on the top by z equals h2 of x, so in other words, give me an x value, I'll stick it in a function and tell you how far up to go. And if the bottom of the function is defined by z equals h1 of x, so again, give me an x value, I'll stick it into this function, tell you how far up to go to get the bottom of this. And let's say that on the x-axis this goes from a to b, then the double integral would be integrated. Let's get the rest set up. Here's the integral of the function with respect to y, evaluated from u1 to u2. So if our region was defined on the top by h2 of x and the bottom by h1 of x, then the next integral would be integrated from h1 of x to h2 of x. Would this be dx or dz? Well, it can't be dx because x is in the limits of integration, so it would have to be dz. And then the last integral would be dx from a to b. Folks, the hardest part about these triple integrals is getting them set up. Once you set them up, it's just a calculus problem. Just integrate, substitute, integrate, substitute, integrate, substitute. So let's take a look at an example in the next video to see how critical it is to set up the problem.